Hello, welcome to today's Knowledge webinar, introducing EikoTwin and bridging the gap between simulation and testing. Imagine what you could achieve if your model predicted a perfect test response. With EikoTwin and image processing, you'll be able to connect test data to your simulation results. Today's presenter, Florent Mathieu, is the CEO and co-founder of EikoSim and has been on a mission to bridge the gap between test and simulation since 2016. I think we'll hear all about this quest from him. And let me tell you a little bit about Knowledge. Knowledge is changing the way designers purchase 3D software. We offer more choices, best advice, faster service, and zero headaches. Check us out at knowledge.com. And now, without further ado, I'm going to share Florent's screen. And so it can take you into this journey, introducing Eiko simulation. Thank you, Florent. Welcome to the Knowledge webinar series. We're very excited to find out about this brand new product on our catalog. We can see your screen.
Thanks a lot. Hello. Yeah.
Perfect.
Well, let's go then. Okay, well, hello everyone. I'm very happy to be invited today to present our solution. As you said, that our idea is really to bridge the gap between test and simulation, and especially in structural mechanics, which is our field of application. Let me tell you first about the problems that we identified at our customers, and the way then I'll present the way we're trying to solve them. First, I'd like to give you a little bit of context about what is called validation. It's called validation, but it's actually simulation model validation. Meaning that for every step of the design and development process of a structure, engineers are going to try to validate the simulation models that they build with physical data, with ground truth, real data that comes from measurements. And in this context, there's a lot of different ways to present things, well, obviously the figure on the left here shows you the classical way to present things with the V shape that going from the top left corner from just system requirements and going down and progressively detailing the structure and explaining how the structure is going to be built, and then going up again. And for each step of this V shape, you want to go back, and this is the arrows in the middle. You want to go back to the design and make sure that the design matches what was expecting and based on the test. But another way to show that is the figure on the right, which I think was made popular by Airbus, at least here in Europe, and shows how for each step of what they call the test and simulation pyramid, you have not only to perform simulations, but also to perform testing accordingly. And obviously it's going to be less and less simulation and testing the more you go up the pyramid. And it shows, I think it's interesting to show how wide this pyramid is at the bottom, and more you go thinning that pyramid when you go to the top. And this is the figure I like to present things on. So you'll see more of this in the next few slides. And the question we're trying to help solve here is, what is validation or model calibration trying to achieve? And obviously, for each step of the pyramid, the idea here is to compare the simulation and experimental outcomes in order to make sure that simulation is not too far from reality and it has some ground truth in it. And if it's acceptable, the model can be used in order to perform further developments. And the question the engineer has to answer is, are the material model close enough to what was expected in the simulation? Is the boundary condition for the simulation valid? Is the shape of the part that I used in the simulation correct? Is it really the real shape or close enough? Or is the interaction model between these two parts correctly? It's not always easy to answer these questions. And validation, the work of validation, which is described in this figure, is to address these questions. Now, how are usually people addressing these questions? Well, it's usually separated into large questions, and the first one is, do you have enough physical data in order to validate the model? For very simple structures such as material samples, specimens, usually you don't need a lot of information in order to validate the model, and you can put usually a very simple sensor, strain gauge, or a displacement sensor, and this will probably be able to help you validate the model perfectly. If you go to higher steps of the pyramids, and especially when you go to very complex simulation models, you're going to have to match a lot of simulation data with as much data as you can grab on the experimental side. And recently, there's been very complex models, very complex geometries and shapes and material models. And obviously, on the test side, it's a little bit less dynamic than on the simulation side, as I could say, because you have basically the same sensors as what you had in the 80s or in the 90s. And this is a limitation because you don't necessarily have as much data as you would like in order to validate a very complex model with these few strain gauges that I show here. This is why I think optical methods have become popular, and this is what we're doing partly at EikoSim. We're developing optical methods in order to help gather way more information than what you have with traditional sensors. This is the first part of the question is, do you have enough? And I think optical measurements bring a lot of data. But there's another hidden question within this this topic, which is, how do you use that data? How do you handle that data? And I think this is very important question, since in this step there's no guide to tell you how to compare the simulation and experimental outcomes. And when you get more and more data points, it becomes really complex to handle that kind of data. If you have one strain gauge, in this case, it's very easy to use Excel or software like this in order to manage the data. It's very simple. It's one column in Excel. If you have more than that, it usually becomes a pain for the engineer, because there's a lot of time spent doing trial and error, modifying the model with changing parameters, and in the end, not always making sure that the model gives the right answer. And the hidden problem of optical measurements for us is the fact that in the end, you don't have a tool to compare the whole set of measurement data coming from the cameras. So most engineers end up taking what they call virtual strain gauges or virtual sensors and doing the same job as what they did in my situation here in the middle, which obviously limits the way that these measurement methods are going to be used. And it's, in a general sense, it's the case for all of the steps between test and simulation. It's going to be a lot of different, what I call do-it-yourself operations, because you have Word documents, you have Excel sheets, you have maps of the how the test should be done on the 2D map of the specimen, and this is taking a lot of time and energy for the engineers in order to match simulation and test data. And this brings a lot of simulation credibility issues, because simulation cannot be improved as much as it should be, and obviously it leads to time overruns, because people are going back and forth between test and simulation and don't always have all of the necessary data at the right place, which is a clear bottleneck in order to make sure that the part is developed in a shorter time. And this is what we're trying to do at EikoSim. If you should put this in a few sentences, we're trying to bring the right kind of data to simulation engineers in order for them to make decisions, and the right kind of test data, obviously. And the way we do that is we put the simulation model, simulation mesh in the middle of all of the validation operations. And obviously this is true for data processing, which is you see on the right. This is also true for test specification, which you will see on the left. Our goal here is to bring a very easy, fluid, fast simulation validation process in order to, in the end, being able to minimize the number of tests that test campaigns handle, obviously in order to cut expenses. The first software we've developed here is EikoTwin DIC, which is image processing and test data management software. It relies on optical measurements, as I showed before. I'll show right after how it works. But the idea here is to align the mesh with the images that are taken by cameras during a test in order to help with image processing, measure displacement and strain fields, meaning a lot of data points with respect to traditional point-wise sensors. But it doesn't stop here, because it's not only about the cameras, and our idea is to collect complementary test data such as strain gauges and other sensors on the 3D model in order to create a package of data that is arranged around the 3D model. The idea here is to make the test data compatible with simulations. And our software gives test engineers the ability to export data that is already compatible with pre-post software that you can find on the CAE side. The idea here is to provide with the tools for what we call simulation-oriented analysis of test data, because it's already provided on the mesh. So as soon as you see it, it's on the mesh, which means it's oriented in the direction that will make people able to compare directly that to simulation data. And obviously, this is supposed to give the ability to simulation engineers to see right away where the model was right or wrong and to correct for it very quickly. Now I'm going to show you a quick video and which illustrates what I just said. Well, these are the questions that simulation engineers are usually asking us or wondering about. So in order to do that, we built a tool that answered this question of simulation confidence and trust, which is central in our approach. And the idea here is to have that kind of measurement, which is not a point-wise measurement. It's a measurement that's taken from the cameras to the mesh, and in order to have usually thousands of measurement points. And all of the color fields that you see here, they're expressed on the mesh, of course, but they're measurements. They're displacement, strain measurements. The idea, of course, being what you see here, create a link between the test and the simulation model, which is usually pretty complex. I mean, we have our customers are usually pretty large corporations, and even they don't have all of the tools in order to compare both data sets. And this is something that one of our current customer calls the two-screen syndrome, with one screen for the test and one screen for the simulation model. And here you have both on the same screen. This is really the main benefit of EikoTwin DIC. Makes the engineer able to have a pathway from the test data to simulation models. I can show a little bit more later if needed, but in this software you can import directly simulation model data. And this is what makes the engineer able to compare directly to simulation results, even within the test lab, which is, I think, interesting. And of course, even if you have a lot of field data, you can also take from this field data pointwise data in order to compare in a more traditional way. This is one of a few of our customers telling how it helped us help them develop their model better. I think what's interesting is usually they one thing I keep in mind is the fact that they. Sorry, I'm going to go to the next slide. Usually this is a nice example of what we've done. For instance, it's in very large structure. In the case of a large structure, here it's what they call a dispenser that holds satellites inside the Ariane rocket. Here the idea is to provide with the test that will be performed on a very large structure, very complex geometry, and one of the goals was to make sure that optical measurements could complement traditional sensors in the right way. This is the kind of map that you can obtain with optical measurements with an EikoTwin DIC. It's as you see, it's on the mesh. Obviously, it's a measurement data, so it's a little bit more noisy than simulation data, but you can see that on this synthetic images, you can verify that the measurement will give the same kind of strain fields as in the simulation. The idea being to make a one-to-one comparison, because obviously you have nodal displacements on the left and on the right that you can compare, and same for strains. You can also import traditional sensors. I'm not going to spend too much time on this. The idea is to show that this is really a platform to aggregate all of the test data. Another software that we have is, I think, is an interesting project that we've had developing this virtual test scene within a software called Blender that you might know about, which is a free software, open source software. And the idea here is to help our customer anticipate and solve experimental problems that could arise when you use a lot of cameras. Here we have, I think on this test, there's been, yes, I think 11 cameras total. Namely, we're trying to do even 20 for next year, which is a pretty large number of cameras. And when dealing with that number, you have to make sure that the test setup will be prepared correctly. So this is really the idea behind this. In the case of this dispenser, we've been able to position all of the camera rigs in order to make sure that we know about the perfect positions for the cameras, which means that the installation procedure itself is shortened. The last software that I think is interesting to show here is Digital Twin, and this more of a beta version right now. And this software is based on the idea that when you have seen the errors that you've done within between model and test, you're going to be able to correct for the model. And one of the ways being, of course, correcting boundary conditions, because they're usually a main source of error, and then change material parameters within the model to make sure that the material that is used in the simulation matches what was seen during the test. I have a few examples now, very short examples to show you the diversity of examples that we have. First one is a vibration test with Safran. What people wanted to see here is how this actuator was resonating at certain frequencies. So obviously in this case we used a high-speed system, 1000 hertz in this case, which helps us capture the sine wave that you see here on the bottom left corner, and obviously compare that result as always to simulation results in order to compare the amplitudes of the sine wave for the simulation and for the test result. Another interesting experiment that we've done was on these lattice specimens, which are additive manufacturing examples of how you can lighten perfectly a material part or part or piece in order to gain weight, especially in aeronautics. And this is a very complex structure, not only in the geometry, but when it's deformed, it has a pretty complex kinematic signature, I would say. So there's a localization band. It's pretty complex to catch and to measure, and obviously with optical measurements, it's way easier than with classical sensors and strain gauges, for instance. Another example here is a car door that was opened pretty brutally in this case in order to test the limits of this structure. It's a Renault car. Again, same kind of experiment, and we've put multi-camera systems here. The idea again was to capture this pretty complex kinematics around this area, which is not very easy to access, and especially when you put a strain gauge on that kind of scene, you always have the question of, is it positioned correctly with respect to, there's no sharp edge to measure where you put the strain gauge from. With that kind of technique, it's way easier to have an overview of what's happening. And finally, another example was from Faurecia with a pretty simple path, actually. What I like about this example is that this testimonial from our customer who told us that usually it would have taken something like a month or at least a few weeks to have the correct simulation model from the test data that they usually have. And with that kind of test data that you see here on the bottom right corner, it took them only a few days in order to calibrate the simulation model. So I think that's pretty impressive, and it shows how just having the right information at the right place at the right time, it brings a lot of value to our customers. And this is my last slide for today. I think when I present these slides, I like to emphasize the benefit that's in the center, which is one of our main customers, Ariane Group. They're really what they say is that they're really willing to help the test lab speak the same language as the engineering office, which really shows how sometimes it's difficult to match physical and virtual worlds. And I really like the fact that they're using our tool in order to bridge that gap, which is really what we're willing to do. Yeah, I think that's really motivating to see that kind of sentence, because it really helps a customer make new connections with different teams, and that's always nice to see. Yes, that was the end for me. Thanks for attending, and I hope I can be of any use to anyone viewing this webinar.
Thank you so much, Florent. You ended with a great quote, and we have no questions for now, so I'm just going to share my slide and remind everybody of Knowledge.com, where they can find the EikoSim product. And I want to thank everybody for attending, reminding everybody that we're on social media, and to check us out at Knowledge.com, because Knowledge is really changing the way designers purchase 3D software. All the choices we have and the advice that you can get on the phone all the time. So really, there's no better place to purchase 3D software. Thank you again, Florent, and looking forward to hear more about EikoSim products. Have a great rest of the day, and bye-bye, everybody.